Okay, so for this video, we will be discussing the applications of the derivative. So the first application that we'll be discussing is the maxima and minima. Okay, so as you all know, so maxima and minima, so those are the values, okay, of a function. So the coordinates of the values of a function where the graph is at its maximum and minimum. So in solving problems involving maxima and minima, so these are the steps. Okay, so these three generally so are the steps in solving problems involving maxima and minima. So the first is we need to obtain the objective function and express it in terms of one variable only. Okay, so if the problem gives us more than one variable, so we will try to express, okay, so the function which we would like to maximize or minimize, so we will use algebraic manipulation to express it in terms of one variable only. Okay, so the next is, so since this is a maxima and minima problem, so we need to set the derivative to 0, so the first derivative. Okay, so and then equate it to 0, and then solve the roots of the resulting equation. Okay, so another also, if we have already solved the roots of the resulting equation, so we use the second derivative test, okay, so to determine if the root that we have obtained is a maximum or a minimum point. Okay, so should add here to use the second derivative test. Okay, so example, so for our first example, we have a number problem. So express 20 as the sum of two numbers such that the sum of the cube of one number and the square of the other is as small as possible. Okay, so we need to solve here the two numbers. Okay, so we are given here that the sum of the two numbers is 20. Okay, and then we also have a condition where the sum of the cube of one number and the square of the other is as small as possible. Okay, so let's try to write that down. So we have solution. So since we don't have any variables given, so we will introduce our variables. Okay, so we will assign. So say for example, we let x as our first number, okay, and then y as our second number. Okay, so the condition was 20 is the sum of two numbers. Okay, so first condition, so x plus y is equal to 20. Okay, so because it is said that 20 is the sum of the two numbers, and our two numbers are x and y, so therefore x plus y is equal to 20. Okay, so next, our second condition says that the sum of the cube of one number and the square of the other is as small as possible. Okay, so we need to minimize, okay, the sum of the cube of one number and the square of the other. So our objective function is for our objective function, so since we have here a sum, so we can let s as the sum. Okay, so the sum of the cube of one number and the square of the other, so s is equal to x cubed plus y squared. Okay, so this is now the sum that we are going to minimize. Okay, so s is equal to x cubed plus y squared. So the cube of one number plus the square of the other. Okay, so you can also express it as x squared plus y cubed. Okay, so if you do that, so later on you will see that you will still solve the same answers. Okay, so this is now our objective function. So from our steps earlier, so express in terms of one variable only. So as you can see here, we have two variables. Okay, two variables x and y. Okay, so we have here s as a function of x and y. Okay, so we need to express it in terms of one variable only. So either x or either x or y only. Okay, so we will replace one. Okay, we will replace one. So using the first condition. Okay, so from the first condition, it says that x plus y is equal to 20. So we can replace x or y in here using this condition. Okay, so but by experience, you will see that replacing y would be easier. Okay, because it's raised to the power of 2 only. So unlike here, it's cube. Okay, so the expansion later on will be longer. So it is easier to replace y in this situation. Okay, but if you like to try it, so you can also replace x. Okay, so it will be slightly more difficult, but you will still get the same answers. Okay, so from x plus y is equal to 20. Okay, so transposing x, we will have y is equal to 20 minus x. Okay, so substituting that in here, so therefore we will have s is equal to x cubed plus, replacing y with 20 minus x, so it will be 20 minus x and then squared. Okay, so this is now our function. Okay, so expressed in one variable only. So now we have expressed it in terms of x only. Okay, so the next thing that we're gonna do is we will expand. Okay, or we can derive it directly. Okay, so here we will be using general power formula. Okay, so whatever you want to do, so it's up to you, so as long as you get the first derivative. Okay, so if you want to expand this, it's also okay. If you want to differentiate it directly, so it's also okay. So but we'll just try to expand this first. So x cubed plus, so 20 minus x squared, so this is a special product, so therefore we'll have first term squared minus 2 times first term times second term plus second term squared, so that will be 20 squared, so that is 400 minus, so 20 times x times 2, so that is 40x, then plus x squared. If you want to rearrange it, so we will have s is equal to x cubed plus x squared minus 40x plus 400. Okay, and then now we set the derivative of s with respect to x to 0. So ds, set ds over dx is equal to 0. Okay, so first we'll solve for ds over dx. So by deriving this, so derivative of x cubed we have 3x squared. Derivative of x squared, so plus 2x and then minus 40. Okay, so since we set the derivative to 0, so therefore we can solve it here maybe. So therefore 3x squared plus 2x minus 40 is equal to 0. So 3x squared plus 2x minus 40 is equal to 0. Okay, so what was the next step after equating to 0? To solve for the roots of the resulting equation. So from this equation, we'll solve for x. Okay, so we can do that by factoring. So we have the coefficient in the first term, so we can multiply it with the last term. So 3 times negative 40. So that is negative 120. So factor negative 120 such that the sum of the factors is positive 2. So it could be negative 10 times 12. Okay, so negative 10 times 12. Okay, so we'll now break down positive 2 such that it will involve the terms with the coefficients negative 10 and positive 12. So it will become 3x squared minus 10x plus 12x minus 40 is equal to 0. Okay, so this equation is still the same with here. Okay, so if you simplify, if you add negative 10x plus 12x is still equal to 2x. So we do that. We separated 2x so that we can group them later on. So grouping the first term, the second term, and then the third term and the fourth term. So we'll have 3x squared minus 10x, one group, plus 12x minus 40 is equal to 0. So next is we can factor the greatest common factor for each group. So the first group, the greatest common factor is, I think, 3. Sorry, it's x. Okay, greatest common factor is x. So x times, so if we factor out x from 3x squared, so what will remain is 3x. Factor out x from 10x, so what will remain is 10. So minus 10 plus greatest common factor here is 4. So factoring out 4, so what will remain here? So factoring out 4 from 12x, so what will remain is 3x. And then factoring out 4 from negative 40, so minus 10 is equal to 0. So next we have, do you call this? Common terms for both the first term and the second term. So we can factor out 3x minus 10. Okay, so what will remain here? The first term, if you factor out 3x minus 10, so what will remain is x. And here, what will remain is 4. Okay, so we have factored it completely. So to solve for the roots, equate the factors to 0. So 3x minus 10 is equal to 0. Another is x plus 4 is equal to 0. Okay, solving for x here. So we have x is equal to, so transposing 10 and then dividing both sides by 3, so we'll get 10 over 3. Here, transposing on the other side, x is equal to negative 4. Okay, so we have two numbers. X is equal to 10 over 3, and then the other one is x is equal to negative 4. Okay, so we have 2 points and we don't know which one of them will give the minimum s. Okay, so which value of x will get a minimum s. So therefore, we have to use the second derivative test. Okay, so let me solve that on another paper. So, okay, so by the second derivative test, so we'll solve for the second derivative. So the second derivative is d squared s over dx squared. So we have here our first derivative, so derive it. So 3 times derivative of x squared, so derivative of x squared is 2x. So 2 times 3, so that is 6x. Okay, plus derivative of 2x, it's 2. Okay, so next is we test these 2 points. Okay, so at x is equal to 10 over 3, so our second derivative, d squared s over dx squared, is equal to 6 times 10 over 3 plus 2. So this will be equal to, so that will be equal to 20 plus 2, so that's 22. Okay, so it's positive, so it's positive, so meaning it's greater than 0, so therefore x is equal to 10 over 3 is the minimum. Okay, so at x is equal to negative 4, so the other point that we have solved, this one, so we'll test if it's a minimum or a maximum. So d squared s over dx squared is equal to, so where was our derivative, so 6 times negative 4 plus 2, so this is negative 22, so it's less than 0, so therefore x is equal to negative 4 is maxima. Okay, so therefore we have solved for x, so now we solved for y. So if x is equal to 10 over 3, then y is equal to, so what was our y earlier, so y is equal to 20 minus x, because their sum is 20. 20 minus x, so we have 20 minus 10 over 3, so this is equal to, so that is equal to 20 minus 10 over 3, so that is 50 over 3. Okay, so therefore our answer is 10 over 3 and 50 over 3. Okay, so if okay, so those are the 2 numbers. Okay, so that's how you apply derivatives in solving those types of problems. Okay, so basically again we follow these steps and then use the second derivative test to determine if what you have solved is a maximum point or a minimum point. Okay, okay, so for our second examples, we have this one, geometric problem. So a piece of cardboard is to be made into an open box by cutting out the corners and folding up the sides. So given a piece of cardboard 12 inches by 12 inches, so what size should the corner notches be so that the resulting box has maximum volume? Okay, so this is a maximum volume problem. So we are given a piece of cardboard. So I believe you are familiar with what a cardboard looks like. and its dimensions are 12 inches by 12 inches. So meaning it's a square. So say for example we have, let me use a finer pen for this. So say this is our cardboard. Okay, so it's a square with dimensions of 12 inches by 12 inches. Okay, and we should cut out its corners. Okay, and then folding the sides so that it will create a box. Okay, so we'll cut out the corners. Okay, so say for example, so these are our cutouts. Okay, so and then it will become like this. Okay, so we will cut out these parts. Okay, so this will be cut out. Okay, and then these sides will be folded upwards, folded inwards. Okay, so if we now let's call this fold up those sides, so it will now become a box. Okay, say for example, so this is the resulting box. Okay, so imagine it looks like that. Okay, so we don't know what the volume okay, so as I've said, so we don't know the volume of this box because we don't have its dimensions. Okay, so here, so we have from our figure, so our variable here are the dimensions, okay, of the cutouts. Okay, so we don't know the dimension of this cutout, so it's variable. Okay, so the length, okay, of the cutouts. Okay, so we can assign that as say for example we assign that as our as x. Okay, so since this will be turned into a box and this will be folded upwards. Okay, so the length of the cutout in this side should also be equal to the length of the cutout of the other side. Okay, so therefore it should also be x in here. Okay, and then all of those dimensions are equal. Okay, okay, so this length of cutout, okay, will now coincide with what dimension in our box. Okay, so the x, I think, would coincide with the height of the box. Okay, that will now be equal to the height of the box. So the height of the box is equal to x. Okay, so the length and the width on the other hand, okay, will become this. Okay, so this dimension and this measurement. Okay, so since all of the this originally was 12 inches, okay, and then this side we're only measuring this side. Okay, so therefore this is 12 inches minus x and minus x. Okay, so this dimension, if we extend those lines, okay, project those, so this will be equal to 12 minus 2x. Okay, and also this is also equal to 12 minus 2x. Okay, so why 2x? Because we have the original 12, okay, which is this, okay, is subtracted by 2x's. Okay, so therefore the width will be equal to 12 minus 2x, and also the length is equal to 12 minus 2x. Okay, so our objective function here is the volume. So we want to maximize our volume. So for the objective function that we want to maximize, okay, so it is equal to the volume. Okay, so our volume, so since this is a box, so the volume is equal to length times width times height. Okay, so our length is 12 minus 2x. Our width is also 12 minus 2x. And our height is x. Okay, so therefore, we can expand this. So it's x times 12 minus 2x squared, right? We can expand that as v is equal to x multiplied by, so this is can apply special products in here. So we'll have 12 squared, so that is 144 minus 12 times 2x, it's 24x times 2, so minus 48x plus 2x squared, so that is 4x squared. Okay, and then we can distribute x, so v is equal to 144x minus 48x squared plus 4x cubed. Okay, so this is now our objective function. Okay, so we want to maximize v, okay, or the volume. So therefore, we get the derivative. So let me write it here. So dv over dx is equal to 0. Okay, but before that, forget that, notice that our function is expressed in a single variable only. Okay, so therefore we can proceed already with the differentiation. So set the first derivative to 0. So dv over dx is equal to, so from here it's 144 minus 48 times 2, that's 96 x plus 4 times 3, so plus 12 x squared. Okay, and then next is equate that to 0. So 144 minus 96x plus 12x squared is equal to 0. So we can factor out 12, I think. So is everything divisible by 12? So 144 divided by 12, yes. 96 divided by 12, yes. And then therefore factoring out 12, so what will remain here is 12 minus 96 divided by 12, so that was 8 plus x squared is equal to 0. So dividing both sides by 12 and then rearranging, divided by 12, so we will have, we want to write first x squared, so x squared minus 8x plus 12 is equal to 0. Okay, so the next is factoring. So you can factor this one. So looking at the last term is 12, so factor 12 such that the sum of the factors is negative 8. So that is negative 6 and negative 2. Okay, so x minus 2 times x minus 6 is equal to 0. So therefore, we have two answers. X is equal to 2 and x is equal to 6 inches. Okay, so the next is we'll try to solve which one would give a maximum value for the volume using the second derivative test. So second derivative test. So we have d squared v over dx squared. So deriving this, so we will have 144, this one, right? So this is wrong. So the second derivative should have been negative 96, and then plus 12x squared. Derivative of 12x squared is 24x. So plus, so this is negative 96 plus 24x. Okay, so at x is equal to 2, so d squared v over dx squared is equal to negative 96 plus 24 times 2 is equal to, so this is negative 96 plus 24 times 2, so negative 48. Okay, so it's negative, so therefore x is equal to 2 is maxima. Okay, so we can also try to solve for the other one. So at x is equal to 6, so d squared v over dx squared is equal to negative 96 plus 24 times 6 is equal to, so negative 96 plus 24 times 6, so we have positive 48. So since that is a positive greater than 0, so therefore x is equal to 6 is minima. Okay, so we want to solve for the maximum value of the volume, and the maximum value of the volume occurs when x is equal to 2, okay, or the length of the cutouts are equal to 2 inches. Okay, so what was the problem again? So let's read. What size should the corner notches be so that the resulting box has maximum volume? Okay, so we're not asked to solve for the volume, so the answer is cutouts should be 2 inches by 2 inches. Okay, so that's it for this problem.